Hello all, let's start section 2.8. Section 2.8, we are talking about related rates. In 2.7, I introduced to you actually from beginning of this chapter that the first derivative of a function actually represents the rate of change. Now, in a real life, how we are using the first derivative to deal with the real world problems. Let me start with a simple example with you. I'm not going to solve this example to the end. I'm just explaining. Then we start with the easy one, and we deal with the complicated ones later. Let's think about, for example, I have a tank of water that's in a shape of a cone, correct? For example, this is a cone. This is the tank of water, and I have water. I'm filling this tank. Maybe it's a city water tank or whatever. We have water inside this tank, correct? Let's pour some water. Let's draw a faucet here, right? This is faucet, the water is coming down to this cone. Our goal with related rates here is to find the rate of change of volume of water, the rate of change of volume of water and respect to time. And respect to time. You know, as time spends, for example, if I have a leak here, if I have a leak and the water goes out, as the time goes on, how much water or how fast the water, the leak is, I want to calculate that. Remember how fast the leak is, I want to calculate that one, and I call that one the rate of change in the volume of water. Few things to see here actually, and easily you can see with your shape. First of all, I have a cone shape. This cone has a height, right? Which I can represent it with H. Of course, this cone has a radius. Let me name the radius R, correct? The rate of change in the volume of this cone in respect to time will be dV over what? dt. As the water goes out like this, the volume of the water is changing. How fast it's changing, we call it the rate of change in volume, and we call it dV over dV dt. Same time, as the water is going down, let me use another color. For example, now I have this much water here. You see the radius is changing. The radius is also getting smaller and smaller and smaller. You see, I have another variable, which is radius, and the change, the rate of change in respect to time on the radius, I call it d or dt. Correct? Volume, rate of change in volume, radius, rate of change in radius. Or another example, there is a water and you drop a rock inside a water. Usually you see you are creating these kind of circles. You practice this a lot when you are near a lake or somewhere and you drop a rock in a water, it creates circle like this and the circles are going out. Great. You can talk about area. The area of the circle, as the area of the circle is increasing, how fast the area of the circle is increasing, you call it dA over dt in respect to time, right? And how fast the radius is changing, or increasing or decreasing, you call it dr over what? dt. We are dealing in this section with these kind of problems in the real life, correct? Let's go back to this con. What you do to calculate, for example, if I ask you to find the rate of change in the volume, it means find dV over dt for me. I'm sorry, dV over dt. How to find dV over dt, how to start, where to start. Your first step is you have to find a related simple formula from geometry or algebra to deal with that formula, correct? Here, I'm talking about the volume of a cone, correct? What is the formula for the volume of a cone? If you remember also, it's in the last page of your book, all these formulas. The volume of a cone equals 1/3 of pi r squared h. That is the simple formula for the volume of a cone. V equals 1/3 pi r squared h. Now, in step 2, after you find your formula, in step 2, what you do, you start taking the derivative of both sides in respect to time. That's important. You are taking the respect of the derivative of your formula in respect to time, because volume is a function of time. A radius is a function of time. Like in 2.7, I discussed with you, velocity was a function of time. Acceleration was a function of time. As time goes on, these functions are changing. That's why we take the derivative in respect to what? In respect to t or time. Let's do it. I think all of you, you know how to take the derivative of this formula in respect to t. But remember, you are using here implicit derivatives because there is no t here, right? There is no t. You don't see there is no t. I take the derivative of both sides in respect to t, but I'll use the implicit derivative to do that. Okay, it means I'll look for the d over dt of v, the derivative of the right side, equals d over dt of, or d dt of 1/3 pi r squared h. The derivative of v, like you see, d over dx of x was 1, correct? D over dt of v gives you dv over dt. Or some teachers are explaining this way. I don't know it's right or wrong. They multiply this v with the top. They say, okay, it gives me dv over dt. But remember your implicit derivatives. When you take the derivative of v, it gives you 1, but you have to multiply it with the, in respect to t, write your derivative dv over dt, right? Which is the same way. Now, right side, 1/3 is a number. I can take it out. I can put it in front of the derivative. Also, pi is a number, right? Then I can put the pi also outside because I'm not taking the derivative of pi. Pi is a number, right? What is the derivative of r squared? D over dt of r squared. D over dt of r squared gives you 2r, because it's implicit, again, dr dt. Correct? Or let me go one more step to make it, maybe you can't see it here, maybe go this way. Okay, I took the constant, which is 1/3 of pi, outside. Now, d over dt of what left inside, r squared h. Here you see you have the product rule on the right side. You have the product rule. You have to apply the product rule. Then dv over dt equals 1/3 pi d dt of r squared gives you 2r dr dt, correct? Times h, because when you have f times g, it's equal f prime g plus g prime f, right? That's your product formula. Then the derivative of the first, which is 2r dr dt, times the second, h, plus the derivative of the second gives you dh dt times first r squared. And if you multiply 1/3 pi to all of them, it's the same, or you can keep it outside like that. I'm not going to solve this example to the end. The reason you see how many variables I have here in this equation. I have to know at least what is the value of dv dt. If I'm looking to the value of dv dt to find the value, the rate of change in the volume, I have to know the rate of change in radius. I have to know the rate of change in height, and I have to know how much is the radius and how much is the height. If I want to solve this problem, I should know how much is height. I should know how much is radius. I should know how much is the rate of change in the height. These values should be given to me. I should know how much is the rate of change in the radius. If they give me this 4 value, easily now I can calculate the rate of change in the volume of the water. I showed just this example for you. It's a kind of complicated one. I want to explain the topic on a complicated one, that you remember how, just the steps, how to start. Draw your shape, translate the language. I don't want to put those steps again for you, but it's in your book, how to deal with the word problem. You learn those stuff in algebra, how we are dealing with the word problem. We read the problem first few times. Then, if it's possible, we draw a diagram of our problem. Then we see which values are given to us, which value I'm looking after. We make a list of them. And after that, we go step 1, write the related formula. Step 2, take the derivative of both sides implicitly. And at the end, plug in the values and you are done. Remember, volume, radius, height, all of them, they are functions of time. Volume is changing in respect to time. Radius is changing in respect to time. Height is changing in respect to time. Then V, R, H, they're all functions of what? Time. Let's start now with the example. I will solve this example to the end for you. This is the easiest one that I will start with. Then we do a few more examples. Example number 1. If y equals x cubed, find dy over dt. But remember, inside the parentheses, y and x are functions of t. Correct? Remember this much? Y and x, they are all functions of t. Y equal x cubed, find dy dt at t equals 1 when x is equal to and dx over dt or dx dt is equal 4. correct? This is the simplest example that I can do for you. And actually this example is not in your book. Now, how to deal with? Start with the given function. The given function is step 1, y equal x cubed. Take the derivative of both sides in respect to t implicitly. It means d dt of y equals d dt of x cubed. d dt of y gives you dy dt equals d dt of x cubed gives you 3x squared dx dt. You see, I'm keeping dx dt because it's implicitly, it's a function of t, correct? Now, as soon as you did this, look, I'm asking in this problem to find dy over dt. I give you the value of x, which was 2, and also I give you the rate of change in x dx dt equal 4. Plug in these values in your resulting equation, and easily you can find dy dt, the rate of change in y. dy dt equals 3 times x is 2 is squared, times dx dt is 4. And if you multiply, it gives you 3 times 4, which is what? 48. Whatever the unit is, 48 centimeters per second, or maybe 48 feet per second, whatever the unit of calculation is, it gives you the rate. Correct? That was your example 1. Let's do another one. Example number 2 from your book. I don't want to write all the example here because it takes time to copy the example. Example number 2. In example number 2, I'm just reading. Air is being pumped in a spherical balloon so that its volume increases. You have a balloon, spherical balloon, like this. Maybe it's a birthday party balloon. Did I draw the balloon very well? I don't know. We are pumping the air inside this balloon, spherical balloon. The way when you pump the air in the balloon, the volume is increasing, right? It's true. The rate of change in the volume is 100 cubic centimeter per second. The rate of change in volume. If I show the volume in V, then dV over dt, or dV dt, represents the rate of change. The rate of change is given to you 100 centimeter cube per second. How fast the radius of the balloon increasing when the diameter is 50? This is the diameter of your balloon, right? It's given as a 50 centimeter. We don't need diameter, we need radius. Half of 50 gives us 25. It means the radius of the volume is 25 centimeter. How fast is the rate of change in radius? You see, when you are pumping a balloon, the radius is changing. The radius is increasing. For example, here, if I show in this diagram, if I pump more air like this, the balloon is getting bigger. It means the radius is changing. The radius is also getting bigger. What they're asking us here, actually, they're asking us to find the rate of change in radius. It means dr what? dt. That's it. What's given, what you're looking, is now clear for you. You have the rate of change in volume, you have the radius, you are looking for the rate of change and radius. The difficult part, maybe on the test day, I'll help you with this, that you need an exact or basic formula for the volume of the sphere. What is the volume, the formula for the volume of the sphere? The formula for the volume of a sphere is V equals 4/3 of pi r cubed. That's your formula for the volume of the sphere. Step 2, take the derivative from both sides implicitly in respect to t. It means d dt of v equals d dt of 4/3 pi r cubed. d dt of v gives you dv dt equals 4/3 pi is a constant, right? It's all number. You see, 4/3 pi, it's a number. I can put 4 pi over 3 here. d dt of r cubed gives you 3r squared. The derivative of r cubed is 3r squared, but you have to keep what? dr dt. That's it. You see, if you look carefully, that's it. You are done. You should plug in the numbers now. Or some students prefer to first solve it for dr dt, then plug in the numbers. Which way is getting easier for you? Go that way. Correct? We are solving this equation for dr dt. Look, you see, you can cancel out 3 with 3 first. dv over dt equals 4 pi r squared dr dt. And if I solve this equation for dr dt, I will multiply both sides by what? I have to get rid of 4 pi r squared by 1 over 4 pi r squared, both sides. 1 over 4 pi r squared. This is algebra, right? It's not even calculus, what I'm doing here. 4 pi r squared cancels out with 4 pi r squared. Then I can write dr dt equals 1 over 4 pi r squared times dv dt. Okay, all the values are given. Let's plug in those values here, and we can find easily the rate of change in radius. dr dt equals 1 over 4 pi times r squared. Your r was 25. 25 squared times dv dt. dv dt was 100 centimeter cube per second, right? I'm not here calculating the units for you. If you want to see, I can put it in different color. Here was centimeter cube per second, and here it's 25 centimeter. If you square it, of course, it gives you centimeter square. 2 of centimeter square cancels out with 2 of them, and you end up with centimeter per second, which is the unit for the rate of change. Let's simplify. I simplify 4 with 100. How many times 4 goes to 100? 25 times, right? And here you see you have 25 square, and here you have 25. It means you can cancel 25 with 25, and you end up with dr dt equals 1 over 1 over 25 pi centimeter per second. That can be your answer, or you can multiply 25 with the value of pi in your calculator, and it gives you approximately, I think, 0.0127 centimeter per cube, centimeter per second. It means the radius is changing 0.0127 centimeter per second. Each second, that much as the radius is increasing. That's the meaning of this problem, correct? Later, when we start with differentiation with integrals, you will see right now we are interested in the rate of change, but there maybe you learn, we are interested when we learn integrals in the value, how much. For example, I have the leak in a tank. How fast is the leak? That's, I use derivatives. How much it will leak, that will be the discussion of integrals, correct? This example was from your book. Let me do another one. It's also from your book. Then I'll stop the lecture. Example 3. A ladder 10 feet long rests against a vertical wall. I have a wall like this. This is the wall, and this is the ground. This is ground. This is my wall. A ladder 10 feet long. For example, this is my ladder. I put it against the wall. I want to climb, clean the window or something, or do some painting outside. This ladder is 10 feet long. If the bottom of the ladder slides away from the wall at the rate of 1 feet per second, if the bottom of this ladder, which is this point, slides away from the wall, it means this way, the rate of change in the sliding is 1 feet per second. If I name the ground x, it means dx over dt is given to me, which is 1 feet per second. You see how I name? I just named it x because it's the x-axis for me. This one, the wall is y-axis for me, correct? I can name this one x, this one y. Now, what they're asking me to do, how fast the top of the ladder sliding down. Of course, when this one is sliding this way, the top of the ladder is sliding down. And I never want to work on a ladder like this because I'll go down and I'm too much scared of climbing on a ladder, right? Because it can happen, right? The ladder is going down. How fast the corner of the ladder, which is on the wall, is going down, it means dy dt, the rate of change in y, how fast. They're asking you to find dy dt. They give you one more information. The bottom of the ladder is 6 feet from the wall. Okay, an important one. They give you the value of x. The bottom of the ladder is 6 feet away from the wall. It means x is given to you as a 6 feet. Now, how to start? What is the basic formula to deal with? Which kind of shape you see here? You see a right triangle. When I'm talking about right triangle, the first formula that immediately jumps in my mind and I'm thinking about is the Pythagorean theorem, which the square of the two sides, x squared plus y squared, equals this side. Let's name this side, for example, L, because that's my ladder, correct? Equals L squared. That's my first formula that I'm thinking. Correct? Now, this is my basic formula. L is given to me. I know how much is L square. L square will be 100. Then I can write x squared plus y squared equals 100. What was your step 2? Step 2, take the derivative of both sides implicitly. And respect to what? And respect to t. Then d over dt or ddt of x squared plus y squared equals d dt of 100. D dt of x squared gives you 2x dx dt plus d dt of y squared gives you 2y dy dt equals d dt of the derivative of a constant is always what? 0. Now, find the rate of change in y, right? It means solve this equation for dy dt. To solve this equation for dy dt, you have to first subtract 2x dx dt from both sides. Subtract 2x dx dt from both sides. These two cancels out, then 2y dy dt equals negative 2x dx dt. Now, solving for dy dt, you have to multiply both sides by 1 over 2y, right? To get rid of y. These two cancels out. Dy dt equals, here 2 cancels out with 2. You end up with negative x over y dx dt. Here you go. You have the value of x, 6. You have dx dt, which was given to you, 1 feet per second, right? The only thing that you don't have is y. But can you find y? Look, your formula is x squared plus y squared equals 100, right? And also you know the value of x, which is 6. Then 36 plus y squared equals 100. If you subtract 36 from both sides, then y squared equals 64 and y equals what? Plus minus 8, but we take only the plus value because y is a distance. Distance cannot be negative. That's why we select positive 8. Now you have the value of y, the value of x, you have dx dt. Plug in this 3 value in your formula and you are done. You can find the rate of change in y. dy dt equals negative x. How much is x? 6. Over y, 8. Dx dt times 1. Dy dt, 1 feet per second. Dy dt equals, simplify, negative. If you simplify by 2, you end up with 3/4 feet per second. That's the rate of change in the corner of the ladder that goes down. How fast? Negative 3/4. Why negative? Because you are going down. Correct? This one was another example from your book that I could use here for you to give you more examples. This was all about section 2.8. Definitely, there are different examples in your book. Follow those examples, solve it, watch the slides. It's even the answer is in the slides that, or then the presentations that I posted for you. You have right now, you have a good understanding of what is the derivative, what is the meaning of derivative, what are the formulas or rules of derivatives, types of derivatives, and also how to use derivatives in a real life. This section was using derivatives in the real life, correct? Which we call it application, or they name it in your book, rate of change. I'll stop the lecture here. See you next time in section 2.9.